We're now going to look at the so-called complete elastic collision in one dimension. In the case of complete elastic collision, say between two billiard balls, one ball comes in this way, mass m1, velocity v1 initial, another one comes that way, mass m2, velocity v2 initial. After making impact, they go their separate ways. They're not stuck together. The conservation of linear momentum, of course, can be applied. So can the conservation of kinetic energy because of the complete elastic collision. So we have two equations, one for conservation linear momentum, the other for conservation of mechanical energy, and that allows us to figure out both V1 final and V2 final. So we can make a complete prediction of what happens after the collision. So let us write down these two conservation laws. The first one, conservation of linear momentum. So Pi equals Pf. You notice I didn't put a vector sign here because, again, that's one-dimensional, so I'm going to use a plus or minus sign, assuming, say, going this way is positive, going that way is negative. So V2 initial, the number that I write down, if it turns out to be a number, that number is actually negative because it goes that way. Okay, so both V1 initial and V2 final, they can carry positive and negative signs. So the way I write it here is M1 V1 initial plus M2 V2 initial. That is the momentum before the collision. It has to equal to the momentum after the collision, and that is M1 V1 final plus M2 V2 final. Now let me write down the conservation of kinetic energy. K initial equals K final. So before the collision, I have 1/2 M1 V1 initial squared plus 1/2 M2 V2 initial squared equals 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. Okay. Kinetic energy before the collision equals kinetic energy after the collision. Now, suppose I know V1 initial and V2 initial. What I want to find is a V1 final and V2 final. This is an equation set. It's got two unknowns and two equations. Of course, we can solve them. The problem here is that the second equation is a quadratic equation. So you're going to have to deal with a quadratic equation set, which can be cumbersome, as you know, because you have to take the square root, that sort of thing. Okay, so let's see. There is actually a good trick for us to solve these two equations without having to deal with the root formula for the quadratic equation, because it turns out by manipulating these two equations algebraically, I can find an equivalent third equation, which happens to be a linear equation as well, which I can combine with the first linear equation right here, so I can solve it without having to deal with quadratic equations. Okay, let's see how we can do that. What I'm going to do is, first of all, you notice that all these 1/2s can be crossed out. And then, right now, both sides have M1 and M2, right? M1 and M2, M1 and M2. So I'm going to rewrite the order a little bit. I'm going to push all the M1s on the left-hand side, push all the M2s on the right-hand side, and that, of course, can be easily done. So let's do that. Okay, so the first formula now reads M1 V1 initial, and then you move that M1 V1 final to that side, so it is V1 initial minus V1 final, right? I factor out M1. The other side, both terms have to do with M2, which I factor out. Here's what's left, V2 final, M2 V2 final. I'm going to move this term M2 V2 initial to the other side, so it's V2 initial, right? Of course I can do that. Now, let's look at the second equation. I'm going to do the same thing. I'm going to move both M1 terms on this side, both M2 terms to the other side. So this side, I'm going to factor out M1. So what's left is V1 initial, that's this term, minus V1 final, don't forget there's squared, minus V1 final squared, minus V1 final squared. Okay, the other side, you got this term left, M2, that's left. And here is V2 final squared. And I'm going to move this term, which also has M2, to the other side. Factor out M2 minus V2 initial squared, V2 initial squared. Okay, take a good look at these two equations. If I call this x, I call this y. So this is x squared minus y squared, right? And what's that? That's x, that's y. So this is x minus y. Similarly, if I call this x squared and y squared, that's x squared minus y squared. Again, this is x minus y. But you know x squared minus y squared is equal to x plus y times x minus y, right? And I already have x minus y here. So how does one simplify it? How do you get rid of the squared? Yeah, the simple thing to do is to make this, write this as x squared minus y squared, and this is x minus y, right? And then I take the second equation divided by the first equation. X plus y times x minus y, and then divided by x minus y. So what do I get? Don't I just have x plus y left? Right? Even m1s cancel. So this side, if I take the second equation divided by the first equation, what's left on the left-hand side is simply x plus y, which is v1 initial plus v1 final. That's it. And the other side, same deal. m2 cancels. This is x squared minus y squared. Here's x minus y. So what's left is x plus y when you take this divided by that. And here I have v2 final plus v2 initial. So what does that third equation read? It says v1 initial plus v1 final equals v2 initial plus v2 final. So it turns out that the sum of the velocities for object 1 before and after the collision equals to the sum of the velocities for object 2 before and after the collision, regardless of the masses. Okay, this is very interesting. So I now have two linear equations. Here's the first one, right here, and here's the second one. Okay, so you see, I successfully got rid of these squared, so I don't have to deal with linear, quadratic equations anymore. Let me then solve these two linear equations, 1 and 2. Now that shouldn't be too hard, right? So let's say we did that. To save us some time, I'm just going to write down the result for you now. And here is the result. v1 final equals this plus this. Okay, this of course can be found in the textbook as well, and we just used two linear equations to find them. I am going to write v2 final here. Now that you know the expression v1 final, can I write down the expression of v2 final? Well, if you go back to the original two equations, okay, equation 1 and equation 2, the original two equations, you find that the index 1 and 2 are completely exchangeable. In fact, if you exchanged index 1 and 2, these two terms will switch, these two switch, these two switch, these two switch. You still have the exact same equation. There is a complete symmetry between indices 1 and 2. So as a matter of fact, if I know v1 final, how do I write down v2 final? I don't have to start from scratch, right? All I have to do is I go back to this equation which has v1 final in it, and let me just exchange the index 1 and 2. Whenever I see m1 replaces m2 and so on. So, what's the second equation? All right, here we go. I continue to write m. I'm going to leave out the index for now. I'm going to add them later. Just copying right here without writing down the index. Okay, there we go. Here comes the index. m1 minus m2, that's for v1 final. Now that I have v2 final, let me exchange the index 1 and 2. So this is m2 minus m1, right? And then m1 plus m2 is just m2 plus m1. 2m2 becomes 2m1. m1 plus m2 again becomes m2 plus m1. v1 initial, what's that? Yeah, it's v2 initial now. And v2 initial goes back to v1 initial. There we go. We found v2 final. Okay, again, we got two equations and two unknowns, so we can completely predict what happens after the collision between two elastic objects in one dimension. I know exactly what's the velocity of object 1 and object 2 after the collision. And they're generally different. Now, let's look at some special cases to see how these formulas work out for a special case. Okay, special case number 1. If m1 and m2 are completely equal to each other. You see from these two expressions, m1 minus m2 would be 0, right? So the first terms here and here, they do not exist anymore. And look at the second term here. What's in the parentheses? 2m over 2m, right? Because m1 equals m2. So that the whole parenthesis is simply equal to 1. So what do you have? You have v1 initial equals V1 final here equals what? Only this left, V2 initial. And similarly, the second one I get V2 final equals only this left, V1 initial. So what is really going on here? The collision between two identical objects, completely elastic collision, yields this result. The final velocity of the first one equals the initial velocity of the second one, and the final velocity of the second one equals the initial velocity of the first one. So guess what? They simply exchange their velocity. That's all there is to it. They exchange the velocity. You see, that's nature's clever way of preserving both conservation of energy and momentum. You see, you go back to the original case. Those are the two general equations, right? Remember now, m1 equals m2. Okay, so if object 1 has velocity v1 initial, object 2 has velocity v2 initial. So this velocity is carried by the first object, this velocity is carried by the second object before the collision. Okay, so they have a certain amount of momentum and energy before the collision. Now, after the collision, you're going to have the same momentum and same energy. But since the two have the exact same mass, does it matter which one carries which velocity? Not really. In fact, if you exchange, if first guy gets the velocity of second guy and second gets the velocity of first guy, they have the same mass, the total amount of linear momentum is still unchanged, and the total amount of kinetic energy is still unchanged. You see? So this is a clever way for nature to preserve both linear momentum and kinetic energy while still doing something, because something did happen, they exchanged the velocity. And in fact, you see cases like that very often. Suppose, say, for example, you play a pool game. Here's billiard ball number 1, and here's billiard ball number 2, right? If you know how to play pool, you know exactly what I'm talking about. Here is, this is the hole that you wanted to strike in. So what you do is, let's say billiard ball 2 is very close to the hole. Now, what you do is, they have the same mass. Okay, so we can consider them roughly as an elastic collision between two identical masses. What you do, you hit it head on. You hit it head on. If you don't hit it head on, they're going to go sideways. It's not a one-dimensional motion anymore. So you hit it head on, and since it's an virtually elastic collision between two identical objects, so what's the result? The first guy is going to acquire the velocity of the second guy before collision, which means the first guy is going to stop. The second one is going to acquire the velocity of the first one before collision, so it's going to fall in. Okay? So as a result, after collision, the green one stops, the red one acquires the velocity of the green one and keeps on moving, falling into the hole. So you see, that's a special case of m1 equals m2. We can see plenty of examples in real life when that happens. Okay, let's look at a second case, special case, and that is when m1 is far greater than m2. Imagine you basically have a Mack truck going this way. It's hitting a tiny bug, okay, tiny, beetle on the road. You know what happens to the Mack truck, right? I mean, what's common sense? The Mack truck hitting a tiny vehicle, much smaller. What happens to the Mack truck? Pretty much nothing. It keeps on going. Okay, so V1 final, that's the final velocity of Mack truck after colliding with a much lighter vehicle. What happens? It's pretty much the same as V1 initial, right? That's according to common sense. Does it work? Does our formula predict that? Well, let's see here. M1 is far greater than M2. So look at the first term here. M1 minus M2 and M1 plus M2. Who cares about the M2, right? M1 dominates, so this parenthesis equals 1. So I have V1 final roughly equal to V1 initial. And look at the second term here. M2 is far less than M1. So this parenthesis is virtually equal to 0 because there's M2 here. There's M1 here, which is far greater than M2. So that's it. V1 final roughly equals V1 initial, which means the Mack truck keeps on going as if nothing happened. That's perfectly agreeable with our prediction. Now, the more interesting situation is what happens to the beetle. Suppose it's an elastic collision with the Mack truck. Okay, V2 final, the velocity of the beetle, the much lighter car after the collision. What do I have here? According to this formula, I have V2 final equals, okay, look at this expression here. M2 minus M1, M2 plus M1. Remember, M2 is far less than M1. Okay, so basically, this is just negative M1 over M1. So you get a negative sign. You get a negative sign, negative V2 initial. Don't forget, there is a next term here. Again, m1 is far greater than m2, so we can ignore that m2 here. So this parenthesis is not equal to 0 anymore. It is equal to about 2, right? Because there's a 2 here. All right, now this is the interesting part. Plus 2v1 initial. So what is that telling us? If you want to consider this term, what does that tell you? After the collision, this is the final velocity of the much lighter, much smaller object. It has acquired its original velocity with a negative sign, which means it just rebounds right back. Okay, so let's say like a ball hitting a wall. Elastic collision, what happens? It simply rebounds like that. It reverses direction of motion. The velocity is unchanged because v2 initial, the speed is unchanged. The velocity is just completely reversed because v2 initial and v2 final differ only by a negative sign, right? They only differ by a negative sign. I'm not considering this term yet. That completely makes sense, okay? If you think about a ball making an elastic collision with the wall, it rebounds right back, keeping its own velocity. Own speed, just reversing the direction of motion. All right? Now, the interesting thing here is the next term. The next term is 2 times the initial velocity of the first or more massive object. In other words, what if this thing is not hitting a stationary wall, rather it's hitting a moving wall, okay? According to this expression here, I must add 2v1 initial. Now, how does that make sense? It's the calculation result. We have to accept it because the algebra is correct, but doesn't mean we understood it. How does one understand this 2v1 initial? Well, actually, it's not that hard. Okay, let's look at let's look at this problem from a different perspective. All right, so here is a far more massive object, and it's making a collision with a much lighter object. Okay, making a collision with a much lighter object, and so here is object 1 and object 2. Okay, v1 initial, v2 initial. Both of these velocities are measured relative to a bystander's reference frame. Okay, say, two cars colliding on a freeway, and I'm the bystander, stand right next to the freeway looking at them. They're both moving. What if I switch a reference frame so that, I'm using car 1, okay, as a reference frame. So car 1 is not moving, right? Car 1 is not moving, and what do I see when I look at car 2? Well, remember, object 1 is the far more massive object. So this is the Mack truck, this is the Beetle. Okay, so here's the thing. From the Mack truck's point of view, the truck is not moving, right? And how fast is the Beetle moving? Well, the Beetle is not quite moving as v2 initial anymore. Rather, if I use some numbers, you can probably see them more carefully, more easily. Let's say this truck is moving at 60 miles per hour. And then Beetle is moving at, say, 40 miles per hour, okay? Say in the same direction. All right. So from the truck's point of view, okay, from the Mack truck's point of view, how fast is Beetle moving? The Beetle is actually moving backwards, right? At what? At 20 miles per hour. And how do you get that velocity? 20 miles per hour backwards. In fact, that's negative because it goes backwards. You basically took v2 initial minus v1 initial, right? So in the new reference frame that's fixed on object 1, okay, v1 initial prime means in the new reference frame fixed on object 1, this is 0, it's not moving. But this other guy, v2 initial prime, right before the collision, in this truck's point of view, is equal to v2 initial minus v1 initial, which in this case is 40 minus 60 is negative 20, going backwards. Okay, this is the reference frame. It's like a wall, and it's stationary. Why stationary? Because you are using itself. You're using the truck itself as a reference frame. Of course, it's not moving, right? So, what does that tell us? It tells us that we're looking at a stationary wall. Okay, object 1 is a stationary wall. It behaves like a stationary wall. So object 2 comes in at 20 miles per hour, closing in, and what happens? Well, common sense tells us if you throw a ball elastically at a stationary wall, it bounces right back without changing the speed, only change direction of motion. So after the collision, we have V2 final prime measured with respect to the truck, object 1, must be equal to negative V2 initial prime, because it just simply reverses the direction of motion without changing the speed. So that is equal to V1 initial minus V2 initial, right? I just reverse it. In other words, positive 20 miles per hour, going that way. But remember, that is measured relative to the truck, which itself is moving 60 miles per hour forward. Okay, let me switch it back to the reference frame of a bystander standing right next to the freeway. From that bystander's point of view, how fast is object number 2 moving after the collision? Well, this is relative to V1 initial, but the driver sees that beetle going forward at 20 miles per hour. What about from bystander's point of view? Well, the driver himself is going 60 miles per hour, so you have to go 60 plus 20, shouldn't you? Okay, that's 80 miles per hour, right? So if I change that to notation, then I find V2 final, not using prime, which means going back to the road as a reference frame. That should be V2 final prime plus V1 initial, shouldn't it? V1 initial. So what is that equal to? Okay, let's see what the result is. Plug that in, okay. You got V1 initial minus V2 initial, then plus another V1 initial, right? Isn't that negative V2 initial, which is this term, plus the sum of these two V1 initial? You see, that is where it came from. Look at this. Isn't that the same as that? Okay, so we successfully achieved an understanding what happens to the smaller vehicle in an elastic collision. Okay, not only did it gets its own velocity reversed, but there is an additional term due to the motion of the much more massive vehicle. If the massive vehicle is not moving, yeah, it's just like hitting the stationary wall, just rebound right back. But otherwise, you have this extra term. So, for example, in this case, going to numerically, car 1 is doing 60, car 2 is doing 40 in the same direction. Afterwards, after the collision, car 2 should rebound after colliding with object 1 at 20 miles per hour relative to this guy. Okay, so relative to the road, it's 60 plus 20, that's 80 miles per hour. And from this formula, we'll get the exact same result, because what? V2 final, which is the velocity of the car, smaller beetle after the collision, negative V2 initial. Okay, V2 initial is this way at 40 miles per hour, so that's negative 40. The first term is negative 40, plus 2 V1 initial. V1 initial is 60 miles per hour. 2 times 60, that's 120, minus 40, what do you get? 80 miles per hour, that's exactly right. Okay, so this is what this extra term comes from, due to the motion of the much more massive object. And in a lot of cases, we can actually utilize this extra term to our advantage. An important application in space aviation is called the slingshot effect. It's actually based on this extra term, which is often overlooked, the so-called slingshot effect. Okay, I don't know if you have seen this movie Apollo 13. It's based on a real story. Apollo 13, as you know, was a doomed mission in the sense that they didn't successfully land on the moon as they intended, but also one of the greatest missions ever accomplished, because despite great difficulties, they were able to get the astronauts back safely on the planet, on Earth. So in this sense, it was the greatest, one of the greatest missions NASA has ever conducted. And here's the deal. On their way to the moon, they found that something was wrong with the spaceship, so they couldn't possibly land safely on the moon and come back. So the priority became to make it safely back. Okay, they were still on their way to the moon. They're still going this way. The Earth is somewhere in the back. So at that point, they had two choices. They can either fire a retro rocket and turn the spacecraft back, or they can keep on going around the moon, in which case they will be doing something like this. like this, fly around the moon like this. So they were both short on oxygen and on fuel. If they had a lot of fuel, then what they can do is just burn a lot of fuel, fire the retro rocket so they can go back. So the first choice would be obvious. But then they didn't have a lot of fuel. Okay, they didn't have a lot of fuel to burn back. So what did they do? Well, what they did was they took the so-called slingshot effect. That was the actual word being used in the movie. They took the slingshot. Actually, they say, take the slingshot. So do you remember? They actually got very close to the moon and came back like this. What is going on here? What's the slingshot effect? You know what a slingshot is, right? Okay, so in this case, the spacecraft and the moon is not touching each other, yet there's still a force between them, even though it's an internal force. Okay, if I consider both as a system. I can call this object 1, this object 2. Obviously, M1 is far greater than M2. That certainly qualifies. That's the moon, that's just the space probe. They're not touching each other physically, but they are interacting with each other nonetheless with gravitational force. I can consider that encounter as an elastic collision. Okay? The force between them is a gravitational force. They're not rubbing against each other or anything. They're not losing their total kinetic energy. Therefore, it's an elastic collision. Elastic collision. Now, object 1 is far more massive than object 2. So after the collision, this V, okay, it comes with V1 initial, right? It comes out with V2 initial, and comes out with V2 final. Is V2 final the same as V2 initial? No, unless the moon is not moving. If the moon is moving with a certain velocity, V1 initial, if the moon happens to be going to moves towards the space probe like this, then according to our analysis, after the collision, after the encounter, the space probe will move backwards. Not only will it gain all its initial speed back with a reverse direction, but also it's going to pick up this extra term 2v1 initial. In other words, it's going to gain twice the speed of the moon going this way. And the moon has to be moving towards the Earth. So therefore, with that slingshot effect, going back, you're going a lot faster than before you picked up this additional term to the motion of the moon. If you wonder, where does that extra kinetic energy of the space probe come from? What do you think? Yeah, because the total kinetic energy of the moon plus the space probe has to be conserved. There's no question that extra energy it gets, the probe gets, must be from the moon. Okay, the thing is, the moon is so massive, it doesn't really care giving this tiny bit of kinetic energy to some much smaller object. So the speed of the moon is virtually unchanged as that encounter happens. And that slingshot effect is frequently used in space probe launches. So you can, for example, launch something, you want to go somewhere there, okay, but instead of going there directly, what you do, you fire the rocket towards a certain planet. And then because of the time of the year, that planet at that time is actually approaching you. Okay, otherwise it's useless. If the planet is approaching you, you can take a slingshot around that planet. In doing so, not only can you explore this planet somewhat by taking some photos, but the other benefit is that you gain twice the speed of that planet approaching you. So you can go a lot faster on your way to another planet you want to explore. That is the clever use of the slingshot.